Find the standard form, center, and vertices of the hyperbola given by the equation. Then graph the hyperbola. Okay, so we need standard form, center, vertices, and a graph. Now, this is in general form. The only real thing I can tell from general form, the fact that the coefficients of x and y squareds are different means it's not a circle. The fact that it has two squares means it's not a parabola. The fact that they're opposite signs means this is not an ellipse. This is a hyperbola. So we're going to take the x terms, group them together, and the y terms, and group them together. I can move the 151 to the right, and now I need to complete the square. First off, I need to factor out the leading coefficients of the x and y terms. So we have x squared minus 2x, leaving a little space, then minus 16 times y squared minus 2y, leave a little space, equals 151. I need to add 1 to complete the square on the inside, but it's actually 9 times 1 that I just did to the left side, so I have to add the 9 times 1 to the right. Similarly, I need to add 1 for the y, but I'm actually subtracting 16. I have to do the same thing on the right side. Okay, so we now have 9 times x minus 1 quantity squared minus 16 times y minus 1 quantity squared equals, and we just need to work this out. You have 151 plus 9 minus 16 is 144. Okay, now we divide by 144 because standard form equals 1 for ellipses and hyperbolas. And we have x minus 1 quantity squared. This 9 and 144 reduced to 16 minus y minus 1 quantity squared over, and 16 over 144 reduces to over 9 equals 1. There's our standard form. From this standard form, we can graph, find the center, find the vertices. Specifically the center. What makes the x squared term 0 is 1, and what makes the y squared term 0 is also 1. Okay, this is a good start. So let's go over here, and 1 and 1, that's our center. Let's label these 1 and 1 so that you can tell the scale of the x and y axes. Now, underneath the x is a 16. That's 4 squared. So this needs to go right 4 and left 4. Underneath the y squared is a 9, so that's up 3 and down 3. So if we go right 4 and up 3, I'm going to put an x, and right 4 and down 3, left 4 and up 3, left 4 and down 3. What we have here are the corners of the box that the ellipse version would fit inside if this had been a plus, but this is a minus of the hyperbola. So now I can dash the lines through the x's and through the center, making what I actually refer to as the x box. These will be the asymptotes for the hyperbola. Now the first term, the positive term, is x. So this is going to open in the x direction. So if it's x squared minus y squared, then it opens in the x direction. If it's y squared minus x squared, it opens in the y direction. This is how the hyperbolas operate. In this case, it's the x. So this point is in fact a vertex, as is this one. So this is 1, 2, 3, 4, 5, comma 1. I'll put that one on the right. And negative 1, 2, 3, negative 3, comma 1. These are the vertices. Now, please don't give a parabola shape, because what these are is these are essentially approximating these asymptotes. They should be getting closer and closer. That one didn't really do a good job. Let's see if I can make that get closer. Oh man, this is hard with this little pen. Let's see. That one's better. And like that. There we go. Shouldn't quite touch this one. You just assume that it's getting so close so fast you can't tell. But if you were to zoom out, these hyperbolas look like X's. It's only if you zoom in do you realize that they curve and connect, and there's actually nothing inside. But they essentially are X's if you zoom out. And so you don't want to give these little shapes because those don't look like X's. They're not parabolas. These are hyperbolas. They're essentially X's. Okay, we have standard form, the center, the vertices, and the graph. I hope this helps.